I'm happy to invite Ben Livneh to the INSAT to present his work. His work is hydrologic prediction through the change in soil moisture and snowpack, estimating natural and how to understand the fluxes. Okay. Ben obtained his two civil engineering degree at University of Western Ontario, Canada. He got his PhD from University of Washington in Seattle, under the guidance from Dennis Lettmeyer. He collaborated with our EMC Irrigation group, include Kemicho, Macaque, Hayden, and I, to improve the irrigation snow model, and also develop a unified land model to merge NOAA energy part with the site hydrologic part. This is his PhD thesis. Okay. And he also developed 6 kilometer irrigation forcing for irrigation domain, where precipitation is being used for national water model forcing generation now by the David Kissinger group, now for the national water model, because 6 kilometers is much fine their irrigation. Our model about 1 degree across, and then include a lot of station from Canada, Mexico. Okay. And his major research system include physics-based hydrology model development, land cover, land use change, snow hydrology, and hydroclimatology. Now he is focusing integrated remote sensing in situ observation to understand how change in climate and land cover will affect water ability at land surface. Now, Ben, time for you to present. Okay.
Yeah, thank you very much, Yulong, and thank you everyone for hosting me here and for inviting me to give this talk, and also for hosting student Ronnie in the program. So I'm going to talk a little bit about a few projects ongoing in my research group today that relate to essentially hydrologic storages, things like soil and snow, and how we can use those changes in those quantities to understand key fluxes that we're interested in. So, as Yulong said, I'm at the University of Colorado. I've been an assistant professor there since 2015, and I have a research group, those of whom I was able to get pictures from are pictured here. There are a couple others. So our major interests are in quantifying changes in land cover and climate impacts on water resources. A lot of this has to do with remote sensing applications and also land surface modeling, for which I suppose my strongest collaborations with Yulong and others are based on. And so these first two folks on the left, Andrew and Ronnie, their work is really going to be featured here today, so I'd like to acknowledge that. Okay, so the presentation will be broken into 3 general sections. The first 2 sections will look at applications of soil moisture variability. And these are centered primarily on this relatively new NASA satellite called SMAP. The first looking at using changes in the SMAP satellite to estimate surface evaporation. And the second is developing a DA framework, data assimilation, to try to predict irrigation magnitude. And this is still kind of in a very experimental phase. Second part of the talk will shift gears a little bit and focus on snow, primarily in the western U.S., and look at how changes in snow cover, specifically projected future changes and reductions in snowpack, what kinds of implications that will have for stream flow prediction. Right. All right. So the first part, using SMAP observations to estimate terrestrial evaporation. So for those of you that are not familiar with SMAP, it is a satellite passive product that actually senses soil moisture in the top 5 centimeters of the land surface. With, I think 5 centimeters is a pretty good number there. So why focus on soil evaporation? So importantly, it helps us develop our models, validate our models, and it also helps us to understand a little bit about this flux evapotranspiration from the land surface to the atmosphere. This is probably the largest flux of water next to precipitation in the terrestrial water bodies. And it just helps us in general understand the water and carbon cycles. So you can see here I've got several components of evaporation shown, evapotranspiration here, and this part of the presentation is just going to focus on soil evaporation here. And so the idea is that by sensing changes in the surface layer, this top 5 centimeters, using the SMAP soil drying rate within a multi-platform framework will allow us to produce a unique estimate of evaporation, which we call ESMAP. And I just want to highlight that the top 5 centimeters there is what we're focusing on. So the way we're going to do this is a very straightforward application of the water balance at the land surface, right? So for a given overpass interval for the satellite, which is anywhere between 1 and 3 days, then we end up with this sort of combination of precipitation being the result of soil evaporation, transpiration, and this flux here, which is the bottom flux, the flux across the boundary from the 5 centimeter depth of the soil, and then the change of storage here. So we can get precipitation from NLDS forcing that many of you are probably quite familiar with. Transpiration, we're estimating using a variation of this Penman-Monteith algorithm used for the MODIS satellite to produce this Mod 16 algorithm. The bottom flux, which is something for which we don't really have direct observations, we're actually using a very highly discretized hydraulic model called Hydrus 1D. And then the change in soil moisture is the part that we get from the SMAP observation. So I'm going to walk through each of those next. Yeah, and the residual term is really the term that we're after, that we're trying to back out of this calculation. So just to show this graphically might be easier to see, we sense the change in soil moisture in the top 5 centimeters from the SMAP satellite. We have an estimate of precipitation in the bottom flux, which can be downward during heavy precipitation events or upwards thereafter, and transpiration, which is always out of the surface layer, and then we get this term E-soil that we're interested in. So you probably have noticed that I didn't say anything about runoff, and so this method is based on the assumption that runoff is equal to 0, and in order to make that assumption, we only are applying this method during those time periods where precipitation is small or 0. And when we make that assumption, then we are able to essentially neglect those 2 terms, leaving only 3 to measure. Right, so the way that this works is we have our water balance equation here on the lower left, and we are observing this change in storage from the SMAP satellite. So imagine that you have these various overpasses at 1, 2, and 3 day intervals. If you have interval without significant precipitation, then we can just apply the water balance equation directly. However, if you had, say, 2 or more millimeters of precipitation, then we would essentially ignore that interval for now. And we have a method for dealing with that that I'm not going to talk about in this presentation. But we can also then apply the water balance method during the other precipitation-free intervals, even if we have, say, less than 2 millimeters or so. And we chose that number because 2 millimeters per day is roughly equal to the uncertainty of the SMAP observation, or the noise in the SMAP product itself. So we're allowing for elements, or for small amounts of precipitation of this level. And the argument here is that if you exclude intervals with a lot of infiltration, then the primary driver of soil evaporation is going to be just the drying, which is the thing that we are sensing. Okay, so going on to the other terms, to get transpiration, there's this fairly complex equation here, which the main things I just want to highlight is that we can actually get most of the inputs from either the annual S forcing or from the modus satellite itself. And what we essentially do is, I'm showing here an estimate of the potential evapotranspiration, which is the environmental demand for evaporation. The blue line shows just the potential transpiration, so that's one component of that. And then if we restrict that by the amount of roots within the surface layer, the top 5 centimeters, there are various ways to estimate root distributions. There are these global analyses that do that. And in general, you have less than 20%, almost always, for any land cover type, of the roots within the top 5 centimeters. So that's another scaling back. And finally, we apply a linear soil moisture restriction, meaning that a drier soil will facilitate less transpiration than a wetter soil. And so then with that, we can get an estimate of surface transpiration. Subsequent term is perhaps the most tricky, which is the flux of water across the bottom boundary of our control volume, and we're calling this Q bar. So this is not measured really anywhere in situ, and most models, land surface models that are widely run, are not really useful for this flux because the discretization of those layers is much coarser than what is needed. And so what we did is we set up this model at a 1 meter depth, and it's a Richards equation type model, and we ran it every 1 centimeter to get this flux. And really, it's based on, when you're in the unsaturated zone, the matrix potential gradient. And all that means is if you have a wetter soil above, then the flow of water will be downward. Also, you can have gravity draining. But if your soil is wetter in the root zone versus the surface layer, you can actually have upward movement of water, which is quite common in the intervals between precipitation. Okay, so what does this look like? So we ran this method at one of the core validation sites for SMAP, Little Washita in Oklahoma. And so what you see here, a couple of things. So the red line is just this top part is just to compare the different products. You've got the Hydrus simulation in red, the in situ soil moisture observations of the top 5 centimeters in brown, and the SMAP observations in blue. So you can see that they actually agree reasonably well most of the time, and they're all kind of independent from one another. So it's expected that they will differ somewhat. Those green bands are intervals where you have more than 2 millimeters of precipitation. So those are excluded from root calculation. And the blue bars are that's the hyetograph from the top. Okay, so this next time series shows the bottom flux into and out of the surface layer. And what you see is that during precipitation events, which are these green bars, you have a lot of drainage. So the bottom flux is high, and that's what we would expect. But shortly after those large events, the sign changes and it becomes positive, which means the movement of water is from the root zone upwards because you have that sort of recovery after precipitation. Surface transpiration, even though it looks big, actually, if you look at the axes are different, and it's actually really quite small here, on the order of tens or hundreds of millimeters. And so the result is shown here. So the black dots are the soil evaporation estimated from this method. The red dots are just the soil drying rate. And you can see that in some cases, the soil drying rate is greater than the estimated evaporation. In some cases, it's less than. And so there's a little bit of also uncertainty in this method, given the merger of 3 independent products. So I probably should have shown this slide sooner. By excluding those times when we have a large amount of precipitation, essentially one question that comes up is, well, how much valid data do we have? And so this map shows the number of valid SMAP overpasses. And this is for a 3-year period, a 2.5-year period, where you can see that in the west, the arid west, up to 80 or 90% of the time you can apply this method, and in the east, less so because you have more frequent storm and larger storms. So comparing the evaporation, ESMAP, to just the soil drying rate at 11 core validation sites. What you see, so the gray dots are just all of the data. The black dots are kind of the mean values. You can actually see that the soil drying and the soil evaporation are really quite similar, which is something that is, I think, heartening in a way. You find that the bottom flux generally approaches zero, and because of the sign changes, in aggregate does not have a large effect, and surface transpiration tends to be fairly small. Comparing our estimate with the NOAA land surface model, this is not really a direct comparison because the NOAA land surface model has a depth of twice that of our product, and you'd expect potentially to have values twice as large. But in general, you see that the soil drying rates on the left and the soil evaporation rates for a big chunk of the western U.S. follow reasonably well. And so there's no real observation here, but at least this tells us that perhaps we're on the right track or in the right ballpark. Right, so to summarize this part of the first part of the talk, ESMAP is a unique approach to estimate one component of ET. This preliminary version is roughly on the same scale of soil evaporation from the NOAA land surface model, which is potentially a useful comparison. And we're currently doing some data assimilation to try to fill in the gaps for the precipitation intervals. We're also looking at key uncertainties because there are quite a few with soil hydraulic properties and evaporative demand. Right now, as you saw, we're doing a lot of validation, and we're in the process of expanding the space and time domain to include the entire United States. And we're writing a paper that we're hoping to submit by the end of this month, but it may take longer, as it often does. Okay, so perhaps we'll just save the questions for the end. Is that better, or should we just have them as we go? That might be better.
I think save one.
Save for the end, okay. Okay, so the second part of this talk is focused on developing a data assimilation framework to estimate irrigation. This work is led by Ronnie, who's here in the audience, and so I just want to acknowledge him there. So if you have any problems with this method, you know who to talk to. No, that's not true. Okay, so irrigation. So why focus on irrigation? Well, it is perhaps, and I would say fairly clearly, the largest consumptive water use in the globe. Right? I've got a map here that shows areas of intensive agriculture. You can see that's a large part of the land surface, and therefore it really alters the water and energy cycles in ways that perhaps, and to extents that people are not quite aware. The magnitude of water that's being used a lot of times is poorly observed. So there's some value to trying to estimate this flux. And so I've got a simple diagram here, and really this work was inspired by the SMAP project, and so we kind of had that in mind. And so the research question is, can we use observed changes in soil moisture to guide estimates of irrigation through data simulation? Okay, so we're sensing changes in soil moisture, say from satellite. In this case, we're actually going to do a simplified version of that. We're just going to test this in model space to see if it's viable. By just knowing changes in soil moisture, can you infer irrigation? Okay, so the overview, the long-term goal is to apply the method to remotely sense soil, something like SNAP. But first, we're just going to use simulated data as kind of a proxy or a surrogate for the satellite data to understand key uncertainties and to test really the viability of this. So the first two parts of this talk are really about testing viability of methods. And we're going to then apply a particle batch smoother data assimilation scheme to do this. And we chose the particle filter because it relies on as few as possible external parameterizations. And of course, mass is conserved and things like that you don't always get, say, a Kalman type of. Okay, so the first step is we have essentially a synthetic experiment, and the first step of that is we apply a known amount of irrigation to the model, and we treat this as the synthetic truth. So this would be like the satellite observation. The nice thing is that we know how much irrigation is put on the model, And the second part is we apply the data assimilation with a bunch of different irrigation assumptions, and we evaluate whether or not the data assimilation can identify the correct total amount of irrigation. So here's a nice schematic here to explain how this works. So as I was saying, you have this synthetic truth. Okay, so this is like an Aussie type experiment for those of you that are familiar, where we apply a known amount of irrigation to the soil moisture. 6 a.m. is the time when the satellite overpass happens, so we're actually applying the irrigation around that time. Then we have an ensemble of different irrigation sources that we apply to the same model. Okay, and you can see the different water levels too. And so we have this range of possible irrigations, because this thing is going to essentially be hidden from the experiment in the sense that we're going to be trying to solve for this. So we're going to be assimilating towards this. And the weights, based on the different soil moistures that we get, we'll apply those weights to the irrigation of each particle that produce the soil moisture. And from that, we'll get a best irrigation estimate. If we subtract the precipitation, because we have precipitation plus irrigation, then we get our best irrigation estimate. This is the goal. Okay, so what does this look like? So I just want to explain how a particle filter works. For those of you that are not familiar, special thanks to Ronnie for creating this nice graph here. So what you essentially have is you get a number of, in this case 4, but in reality you have like 100 of these different soil moisture time series, right? So the pink, blue, brown, and green lines. And you can see that they go up every time you apply irrigation. So we're calling that P here because it's like a precipitation force. Okay. And so what happens is you have your observation here, which is in red, which is in our case is this special simulation that we call truth. And you calculate weights. So around each, so these are the different irrigation or precipitation forces for each particle. Each simulation is called a particle in this framework. So around each particle, at the time of the observation, you actually have a probabilistic estimate of the sort of performance of that particle. So the weights are not done linearly, instead they're done in a probabilistic context. And so you have one of those for each of those, and you end up with a weight. So each particle gets a weight based on its distance, not linearly, but in a probabilistic way from the observation. You do that at one time step, you do it at another time step, and then you get this accumulated weight. It's a product of the two, and then it scales to 1. So you probably won't be able to do quick enough math to make those, to sort out those numbers. But they do add up in sort of a product fashion. And so then what happens is you can take those weights and apply them to the different particles and use their precipitation forces to get a total amount of irrigation, or a total amount of precipitation. And we do this on a 2-day fixed window, I'm showing here, but in reality you can do a longer window. And the reason for a shorter or longer window is to capture higher or lower frequency variability, right? Because if you have very noisy data, you might not want to be treating each instance, but rather groups of instances, so you don't lose the long-term variability, and then you repeat. So that's how that works. So we have this case study. We're using the Vic land surface model, single grid box in a catchment in Nebraska. From the aerial photo, you can see that this is a highly agricultural catchment. It does indeed get quite a lot of irrigation. Ronnie pulled a report that detailed some of the information on the amount of irrigation that we may expect. So we applied roughly 700 millimeters over the course of one season to this project, to this test case. Now, there's a lot of layers here, and a lot of sources of uncertainty. So in the very first case, we assume that we have a daily satellite observation, which is our synthetic truth. But in reality, we know that actually observations happen irregularly, every 1 to 3 days. So we evaluate the performance at all these different levels, we know that the satellite has noise, right? So we introduce noise into the synthetic observation of several percent. And then we also know, importantly, that irrigation time is often unknown. It can happen between, say, 5 a.m. and 10 a.m. based on the literature. But we don't know exactly when it's going to happen. Is it going to happen if the satellite, for example, overpasses at 6 a.m.? You may have the irrigation happening before that. That would be ideal. Or after, which would be more problematic. The last part is there's a fair bit of model uncertainty, right? So we're treating our model like a satellite observation. But in reality, the satellite is quite different from the model in terms of its characteristics, its statistics, or its parameters, if you can say so. We haven't quite figured out how to show those results yet, so I'm not going to show the results from the model. I'll show the other. All right. So this is a demonstration of the daily data assimilation. So the red circles are the sort of observation, synthetic observation. And then we have 100 different gray lines, which is 100 different simulations with different precipitation forcings, the black being the best estimate. So based on these weights, you get the best estimate. And you can see that it does a reasonably good job. We're using an 8-day window here, I believe, to capture the variability. And now, that was soil moisture. What we're really interested in is irrigation. So this shows the same, for the same 100 particles, you have 100 different possible irrigation amounts. And the black line shows the truth irrigation. This adds up to about 700 millimeters. And so when you apply the methodology, actually you get a pretty good result in terms of relatively low bias and high correspondence. Right? So it suggests that this method could be viable to estimate irrigation. Now, of course, this is for daily, right? And we don't have too many satellites. Well, certainly the SMAP satellite does not overpass every day. So what if we actually change that to a 1 to 3 day overpass? And when you look, the results are really quite similar, and the statistics are also quite similar. I think they're noisy enough that actually there's enough, I guess, variability in the method that those numbers are essentially the same. The next step that we looked at was, well, what if we have larger signal to noise? So the model, what we did is we introduced a observed noise of 1% to 5% RMSE into the model, and we reran the method. And what you can see is as you get to the larger noise values, like this green line, these are departures and these are errors. The errors start to get larger. And in this case, we got a percent bias on the order of just under 10% and a lower correspondence, R of 7. So this suggests that for the very largest errors, you start to really degrade the performance, but it still gives actually a fairly good representation of the irrigation. I think in reality, the SMAP satellite has something, I think the published value is 0.03. So somewhere in there. And now the last part that I'm going to talk about is this issue of unknown irrigation time. Right? So imagine that your satellite passes over at 6 a.m. Okay? And you don't know when the farmers are going to apply the irrigation water. Is it going to be maybe at 2 a.m., maybe at 3 a.m., maybe at 10 a.m., right? And so there are these instances which are particularly problematic where the irrigation gets applied after the satellite overpass. Because if you imagine that all your information is gathered here, then if you have irrigation applied after that, you won't really, the satellite won't sense it until the very next overpass. At which point, a lot of the signal has dissipated due to just the drainage of the soil moisture in the soil. So when we actually run these different cases through, it turns out that if the irrigation is applied before the satellite overpass, so 2 to 3 a.m. or 4 to 5 a.m., the performance is actually quite good because that information is captured in the satellite overpass. However, if the overpass, if the irrigation happens after the overpass, then you start to see these larger errors, and that's because a lot of that water has already dissipated by the next satellite overpass. And this is really getting into some potentially poor performance, maybe less than 10% of the variance is explained here. So this is really an issue. So that's kind of a work in progress. To summarize, the particle filter, I think, is a unique approach to SMAP irrigation. This method shows promise, but there's a few key uncertainties still to be resolved. Moving forward, the irrigation time is perhaps the most significant issue. Ronnie is exploring this two-stage method that can first estimate the time of irrigation and then look at the magnitude after that. The last part, which I didn't talk about, is this issue of model uncertainty, where the satellite is kind of like a model and we don't know the parameters, and we're looking at ways of expressing that. And that appears to be about equally important for the irrigation timing there. So now I'm going to switch to the last part of the talk. Hopefully everyone is still with me here. And this is talking a little bit more about water supply and water supply prediction. So the question here is, how will changes in projected snowpack affect our ability to predict stream flow? So this is part of a project that I'm leading, focused primarily in the upper Colorado River Basin, where we've actually conducted interviews with water managers in the region and asked them questions about how they manage for drought specifically. So if you're in a drought year, what kind of data do you look at? And snowpack was identified as a key predictor for that. So we all kind of have a sense that future snow projections are somewhat, maybe they will be somewhat diminished because of warming. And so the question is, are snowpack sensitivities are these snowpack sensitivities going to be basically problematic for streamflow prediction? And even though I started this project looking at the upper Colorado River Basin, we ended up looking at the western U.S. as a whole and looking at how the two areas came together, although the primary focus was in the upper Colorado. Right, so the first part of this research was led by collaborators, social scientists, and they were asking these types of questions about awareness, the types of investments that these irrigation and other water managers are making into drought information systems. And we really needed to better understand how managers are managing this resource. And then the last part is the uncertainty around this indicator, snowpack, in terms of is it robust to predict snow presently and into the future. So this, you can see a map here of western Colorado, the West Slope as we call it, and some of the agencies there. So my collaborators did these interviews, and they did a bunch of different analysis, decision-making meetings that they attended and so on. And really what they found was that snow water equivalent, especially in the spring, so like April 1st, for example, was identified as the most reliable source for water supply forecasting. This is consistent with an earlier study that we did where we actually interviewed over 100 state leaders. And this is through the Western Water Assessment, where I'm a PI. Okay, so moving on to the physical science, the question really here is how will the predictive power, predictive values of snow information change in a warmer world? Okay, so you have, the first step is to establish a baseline. So evaluating the predictive power of historical snow observations to forecast warm season streamflow. So you'll take spring snowpack, say at April 1st, and forecast streamflow during the warm season, April through July. And we're doing this with observations and with models, because when we go to the future, we only have models. We don't have observations, of course. And so we're looking at then the change between the future and the historical. And this is a map of the upper Colorado Basin, 100 or so snow-tail sites and stream gauge for the entire upper basin. Okay. So the predictive power of snowpack. Snow is used typically in two ways to forecast warm season streamflows. The first is by initializing numerical models, so land surface models, hydrologic models. The second way is as a predictor in statistical equations that relate April 1st snow to warm season stream flow. Okay? And this has been done fairly routinely by the NRCS, for example. And I'm just going to focus on the statistical analysis today because it's a much cleaner, I think, way to attribute the value of snow rather than getting into some of the model physics and so forth. Right, so as I was saying, the NRCS has these official regression equations where essentially they try to predict stream flow, which is Q here, warm season stream flow, as a linear combination of station data that observe snow water equivalent and precipitation. And essentially what they do is they estimate these coefficients, and using those coefficients then they can make a prediction for stream flow. For this talk and for this analysis, I'm just going to focus on this first part, the influence of snowpack on stream flow, because snowpack is really the thing that is projected to change fairly greatly. So here's an example. Okay, so this is one of the tributaries of the Colorado River. I'm showing you a graph of April 1st snow water equivalent. Year to year, there's like 16 years or so here. And you can see that there's quite a bit of interannual variability in the snowpack. This is the predictor in the equation. And so you can see the variability there. The next thing is the target, which is April through July observed flow. And you can see that the flow also rises and falls kind of in a similar way. So these things are really related. Much of that water that ends up in the stream originated as snowpack. And so that's the basis of this method. So then we develop a very simple predictive flow model using something called singular value decomposition, which is very similar to principal components regression, which is what is used by the NRCS. And we create this red line here, which captures a lot of the variability just based on the snowpack. Okay, so that's the basic method. This is the basic equation. And it's really based on these station locations. So I'm showing you here some different stations with different colors. And so for the Colorado headwaters, these would be considered low elevation stations, 8,000 to 9,000 feet. You also have different elevations, moderate or high elevations, 10,000 to 11,000 feet. And one question came up was, are these stations all going to be equally robust in terms of their ability to predict? If you think about lower elevation stations versus higher elevation stations. So we tried to suss this out a little bit. And basically what I'm showing here is trying to answer this question, is are higher elevation predictors more robust? Climate warming comes later. This is just historical analysis, 16 years or so. So what I did was I ran this equation here, and I ran it using just one station at a time. And that is shown here in where we have 1. Then I used combinations of 2, 3, 4, 5, and 6 stations to try to make this prediction. And this is the vertical axis is the normalized root mean squared error, smaller values of them. And the color of the dots represents the mean elevation of those stations. And so what you find in general, what we noticed was you tend to get more bluer, more higher elevation stations having smaller errors. And we thought maybe that this actually is a broader phenomenon here. And so we wanted to look at this under climate warming. So what we did is we took future climate projections that were hydrologically downscaled using the Vic model, 29 CMAP 5 projection. We looked at April 1 SWE from the model. We actually compared the historical simulations with snowtell observations, and we actually found pretty high correspondence, so an R of 0.93 for 133 stations. There was a persistent bias, but in general, the variability was strong enough that we felt confident in these data. So this map on the left shows the expected changes in April 1 SWE relative to the historic. And so you can actually see a bunch of reds, which means we're going to have less April 1 SWE. But yet, actually, on the west slope, where we're actually interested, these orange outlines, a little hard to see, you actually also get some blue dots. And this is because the CMAP 5 projections show a drastic, sharp increase in precipitation in this part of the country. And so that increase in precipitation seems to offset a lot of the warming at some of these high elevation stations, so you actually get more snow rather than less. Okay, so now I regenerated this graph, except now we're using simulated snow water equivalent and flow from the variable infiltration capacity model, which has a full water and energy balance snow model. And the circles here are the historical, and the triangles are the future climate. And what we actually find is a pretty strong correspondence between elevation and performance, and streamflow prediction performance. If you calculate a rank correlation among these, so between the error and the elevation, you actually get a very strong correspondence, even out to, I think, 4 predictors. And so this suggests that there is very much a very real relationship between elevation, which essentially is a proxy for air temperature, how cold things are, and predictive skill. And if you look at drought years, coming back to the whole purpose of this study, you find that you actually, compared to regular years, you tend to have larger errors than in normal years. And the thing with drought is it really depends on how you calculate the performance metrics, because there are many ways to do this. And if you look at it in one way or another way, you can get different performance measures. So because prediction errors in drought years are largely depending on the evaluation protocol, is it leading squared errors, is it bias, is it correlation, and other things, we decided instead to use something called the equitable threat score. This is a categorical performance metric, which means it says, was it a drought or wasn't it a drought in observation? Then did the model predict a drought or not, in terms of a 25th percentile or 20th percentile extreme confidence. And so then you can actually go into one of this matrix here where you have hits and misses. So did you correctly forecast drought? Did you correctly forecast no drought? Or the other 2 types of errors? And we chose the equitable threat score because it also has this random component, which means if you were, say, in a very wet climate, you would, by sheer randomness, correctly predict that it was going to rain if it was a very rainy place. And so this tries to account for a little bit. A higher number is a better score. So then what we did was we wanted to see how the drought prediction changes going out into the future. So kind of like what they do at the NRCS and the Colorado Basin River Forecast Centers, we calibrated this equation over 30 years, and then we applied it to the next 5 years, starting with the historical period and marching up every 5 years, because these agencies, they update their calibrations every 3 years. So we wanted to make it consistent so that when we're out at 2100, we're not training our model with the 1900s, we're actually training it with the most recent data so it reflects the changing hydroclimate.
Excuse me, someone is typing and without muting. It's very annoying. Please mute yourself. Thank you.
Thank you for that. So so this is what you end up with. This is the drought equitable threat score. So warmer colors tend to be poorer performance. Cooler colors are better performance. I apologize that the way that this graph appears is a little bit hard to see. But essentially in the historical period on the left, all the way going to, you can see a lot more blues and greens. And then as you go to mid-century and late century, what you tend to see is that the ability to predict drought tends to get worse and worse in certain areas. The upper Colorado River Basin and actually the headwaters of the Columbia River Basin tend to kind of be uniquely resilient in this context. Looking at difference maps, which is probably easier, this is the change between mid-century and historic and late century and historic. And what you can actually see is that, so the red colors mean drought prediction is getting worse. Blue colors mean it's staying the same or getting better. So you can kind of see the same trend. The maritime sort of climates are really getting worse. Some of the interior and especially the high elevation stuff appears to be holding roughly steady. And one way that this can be understood is by the relative retention of snow on April 1st. Right? So the blue colors now show places where you have more April 1st conditions with 0 snow in the future, right? Or the change going into the future. And so anytime you have a 0 for SWE, which is your predictor, it really hurts the performance of the model because you can't really predict something if 0 is your predictor other than you have this intercept. So really I think what's happening is the cooler, higher elevation areas in the interior tend to be retaining more snow and therefore seem to be better suited to predict this kind of drought. Right, so to conclude, drought risk management, which I didn't talk a lot about, is a pretty complex landscape. I would say even more complex than all the physical science I've shown today. And there's an entrenched reliance on using local snowpack information that isn't going to change. It looks like stream flow predictability is elevation dependent, and future snowpack predictions in the upper Colorado River Basin, which is for whom, the stakeholders for whom this research was done, appears to be uniquely resilient, which is kind of not the result we were expecting, but is the result we got. I'm currently writing this up, hoping to also submit this paper this summer before classes begin. And so I'd like to acknowledge the contributors, as I said, Ronnie, Andrew, some other folks at University of Colorado, and these 2 nice grants that help to support this work. So thank you very much.
Okay, thanks, Ben. Any questions from your back?
Hello, my name is Lindsay. Fellow I have a quick question regarding the irrigation. How would you take into account when there are farmers such as in the southern plains that have non-stop irrigation during the year? When there's irrigation 24/7, and there isn't a gap between. How would you account for that?
That's a really good question. That is something we have not looked at yet. We're starting simple, starting with like all the irrigation happens in 1 hour. I think Ronnie's looked at cases where the irrigation happens over several hours. But we haven't looked at the continuous case, and that's an interesting case.
Yeah, it's very common within the southern plains to have for farmers to irrigate 24/7 for like 3 months at a time.
Wow.
Between July and September.
And is this sprinkler irrigation? Is it flood?
Sprinkler and flood.
Okay. Yeah, because I know you can also have, for example, drip irrigation, which we wouldn't be able to really detect. I don't think. But that's a good question. Definitely should look, as we expand the spatial domain, we should definitely look at that case.
Thank you for that. For the first part, integration estimate. So we use 5 centimeters for depth.
Yeah.
In general, ESMAP largely depends on the weather. What dry,
Yeah.
and also depends on the factory type, gas and high temperature. So my question is, have you used the loss in another different area and also different applications?
Oh, I see. Okay, so the question is that the first part is that actually this 5 centimeter depth is variable based on things like moisture content because of the dielectric properties and so on. And so we haven't, basically, as the first step, we've just treated that as the total depth. We have, so we're not varying this 5 centimeter. We have the capability, though, with the way the model, the Hydrus is set up every 1 centimeter, that we actually could look at the variable depth. If we had good information on what that, I don't know if there is good information on how deep or shallow that sensing depth is. If people have looked at that, but if we got that information, we probably could use it. For now, we're just keeping it really simple, acknowledging that it is actually going to be a variable. Yeah. Yes.
That's good talk.
Thank you.
Yeah, I'm having trouble just understanding
couple of things there. So I know that anytime you have very dense vegetation or steep terrain, then actually the satellite doesn't work well, and those areas get screened out. There's like a quality flag that needs to be applied. Like, yeah, like I think usually that's reserved for fairly dense forests. When you have grass, so it's a passive microwave. I'm not sure what the frequency is. Somebody here can Elvin, that therefore can penetrate through some vegetation, I think, to some level. But so what it's seeing then, I guess, is every 1 to 3 days. It's essentially a function of the moisture content, because that affects kind of the brightness temperature, which I guess is what is the sense. So the impact of vegetation, I think, is kind of a tricky thing, right? Depending on how much is it going to affect the signal. I don't know that much about that. The details of the signal processing. I don't know if somebody else knows about that. So, but yeah, that's a good question. So what are you actually sensing? Is it the vegetation moisture or the soil? And I think there's, based on the core validation work that has been done, there's strong reason to believe that in places like grasslands or even shrublands, you are capturing a large part of the soil moisture variability when you compare the satellite with the soil moisture.
Yeah. But so if I understand, the soil moisture observations are not used very much, other than maybe for validation of things like this. I'm still trying to wrap my arms around why soil moisture observations are not similar to the model.
Yeah. Well, you don't have too many soil moisture. Oh no, that's fine. No, I think that one of the challenges with soil moisture observations at that shallow of a depth is those tend to be problematic, because the hydraulic properties and everything else are quite, you can get quite extreme values for the very shallowest soils that would be representative of this. Often you'll have a soil moisture probe at 5 centimeters would be the shallowest. And that's probably more representative of maybe the top 10 centimeters than it is just that surface line. There's a few other satellites kind of like SMAP that sense sometimes even shallower, like this ASCAP, SMAP, something like that. And I think your suggestion is a good one. I think that there's a desire to kind of have something that's independent from in situ data for the obvious reasons, filling in places where we don't have data. But I think it's just a kind of a perennial problem. How do you integrate? Because you have the in situ data in some places.
If the in situ data basically is how big the box represents. For example, in situ you specific for given soil texture, but for a big box, I have different. How do you use it? This is the soil moisture is quite different animals with other like This is more continuous, it's very variable.
Yeah, so the footprint of the satellite is maybe 10 kilometers on the side, and these in situ probes are maybe in one small part of that footprint, where maybe you have a sandy patch or a patch of a lot of clay that may not be representative necessarily of the whole area. It is a tricky, this whole scaling and representative issue is a whole other part of the limitation. I think it's a good point.
One of the things that we're trying to do here is figure out how to assimilate land surface data, and so that's what I understand is how representative are the mechanisms of that. And assimilate just assuming that there's small radius of influence, for example.
So in places where you have a fairly high density of these observations, you can look at the kind of the decorrelation lines. And that's one way, and Ronnie, I think, part of his work here, he's looking at some of that. And what you find in the entire U.S. is that, I'd say very off the cuff, maybe about half of the observations seem to be representative enough that you could compare them with like a 10 kilometer. The other half seem to be much noisier. Just the variability is much different, and in the local versus the kind of place.
We are talking about the soil heritability, right? We have a map of the soil that can take a look at what kind of soil you're using for soil moisture retrieval. I'm just wondering.
Yeah. Well, so one of the things we've done with our project is, what if you say you're at a point and we're running this one-dimensional model? What if you run it with all the different soil types? How much does that matter? Right? In some places it matters a lot. There are these maps, for example, StatsGo, CIRES is another one, and those are good to varying degrees. I know people that have, went and put a shovel in the ground where it says it's going to be cut, and it is cut. But another place you do that and it isn't.
It's only fine.
Well, yeah, and sometimes there's deeper horizons. I think that's something we're actively interested in, is trying to classify the different soil types in combination with this method to get it to a hand better.
Any questions from the online audience?
Hi, Ben. This is Gary. I have a couple questions.
Yeah.
First is I'm very interested in your PBS method, and can you group can do some work and can apply your PBS into our NOAA model? And currently, I know it's for your weak model. You use the weak model. Can you do something with NOAA model and to assimilate, for example, the snow, and to see compare with the currently used UKS method?
Yeah, I think we're actively interested in that. Part of Ronnie's interest is to try to extend some of these methods into something like this, I think, in the long term, where you already have this built-in data assimilation capability. Maybe the unsolvable or the Kalman method, maybe there are places where it's better to use a different method. But I think so. I think it's a kind of a medium or longer term goal, and there's no reason why you couldn't apply it to NOAA or any other model.
Okay. And the second question is for the last part, and it's very interesting. And you explore some like downstream method, to give maybe a more accurate estimate of snow. So that may be very interesting to apply your method into some course or even observation, to generate some high resolution snow product. That may be very interesting in the future for us to use.
Okay, yeah, I think there could be something there to do. I'm not sure exactly what the very next step would be, but it sounds like there's some potential there.
Oh, okay, thank you. And could you maybe send our land group your manuscript to something, the publication?
Can you repeat that?
You have some draft, right? And for your work, some of your work, and we appreciate if you can send us your manuscript.
Oh yeah. Yeah, so as those become finalized, if you notice, they're all listed as in preparation, but they're all getting very close. I'd be happy to share them with you though, once they're finalized. Yeah.
Okay, thank you.
So we can post your presentation from our website, right?
Yeah.
So maybe you can add some reference or something.
I think so. Okay.
Yeah, maybe that's my
Okay, any further questions for online audience?
thing.
Okay, any questions from audience? If not, I have one more question. For example, you talk about survey and elevation relationship. Do you think because of the higher elevation, your survey will be larger, and then and then store a lot of signal because the cold and then the melt is slowly and then they have a slow physical process and then eventually is related to summer warm spring prediction.
Well, I think it's two things. I think it's that, meaning you have more water stored at the higher elevations, so there's more signal. But the other part is that the amount of times when you have no snow at the highest elevations is almost never. So you almost always have snow up high. So you almost always have some information that you can predict. Versus, I think at the lower and intermediate elevations, you have some years where you don't have any snow, in which case you really are not able to predict. Okay.
You try.
If you add in precipitation, will that help you predict the simple based on lower,
Yeah. So we repeated this with accumulated precipitation. So again, in general, the main two predictors are April 1, let's say, snow, water equivalent, and accumulated precipitation from like the whole water year up to April 1st. And we find that predictions get better everywhere, but often only by a small amount, because in many places, the precipitation that you accumulate is either stored as snow if it's cold enough, and if it's not cold enough, then a lot of that water tends to run off before the forecast season. But you do get some improvement, but it was smaller than we thought, maybe like 5 or 10% improvement or something. Of course, that 5 or 10% is going to be really important if you're losing a lot of snow. So. But yeah, and then there's other predictors that people use, like the phase of ENSO, or temperature, or soil moisture, different things. Yeah. So we may explore some of those too.
Okay.
Thanks.
Yeah, thank you very much.